Hey everyone! Today we will be implementing the double DQ learning algorithm. This is going to be basically a very tiny iteration on top of the original DQ learning stuff that we've already looked at. So the DQN implementation we did earlier is a prerequisite to this. There's going to be a lot of code, about 95% of the code is repetition. So we're not going to re-implement the replay buffer or the model or any of that stuff, because we don't need to. It's all identical. We're just going to make the couple of changes necessary to reflect the double DeepQ learning algorithm, and then in the future we'll also update it for the dueling DeepQ learning algorithm. So these should be pretty short videos just to kind of get you going with the main idea of some of these architectures and algorithms. And so let's go ahead and start. So if we remember from DeepQ learning, we had to solve this thing called the moving target problem. And so what was the moving target problem? The issue was that we had this neural network, the Q model, let's call it, that takes some state features and it produces a Q value for the different actions. And so what we did is we passed in our state features for the current states and we got the Q values for the current actions, right? That was our estimate. And then similarly, we passed in the next state features, got the Q values for the next actions, and then we used that to compute our TD target, right? And we basically did the max over that, and that gave us our TD target. Standard setup. The problem is this: as we update this model, both our Q values will continue to change and our TD targets will continue to change. So we're trying to minimize the mean squared error between my Q values and its TD targets because we want the TD target as it's representative of my future expected rewards, and I want my current state action pair to be close to that future expected rewards, right? And so the problem now becomes, if this is changing and my TD target continues changing, well, if everything is changing, then how do I minimize the mean squared error between it, right? You can imagine that as my TD target continues to shift as this model changes, then my Q values will struggle to minimize the mean squared error. There's just not something for the model to hold on to, right? That's essentially the problem. So my TD target, as it continues moving, it's hard to minimize some distance to something that continues to move. And this leads to unstable training. And so to solve this, we essentially created a duplicate of the model. We had a Q model and we had our Q target model, and they were identical in every single way. And the Q target model was never trained. It was held frozen, and we periodically updated it, right? So periodically we just copied the weights of our Q model into the Q target model. And so now we've done a separation. We use our Q model to estimate for our current state action pair, right? So we pass in some states, we get some our Q values for the different actions, and there we go. On the other hand, the Q target looked at our next states features, right? Next states, and it produced some Q values for the different actions of the next state. And we used this to compute our TD target. And the benefit here was that this Q target was held frozen for a couple of iterations. So no matter what this Q model up here was doing, as long as we passed in the same state features right here, next state features right here, it'll always produce the same Q values for the actions for the next state as well. And so essentially, the TD target that we were computing is held constant, right, effectively constant, for a couple of iterations. And by doing this, it gives the model an opportunity to have these Q values essentially minimize its distance to my TD target. And then once we've done a couple of iterations, we can go ahead and update it, right? We can update our Q target with this new information that our Q model has learned. And that's the main idea behind our stable training for deep Q learning, right? That this was essentially necessary because training had to be stabilized in some meaningful way. So now instead of having a moving target problem where our target Q values just keep changing every iteration, now they only change every couple of iterations. And that gives our model some time to essentially minimize that mean squared error distance. This leads to a completely different problem though, and this is what the double DeepQ learning algorithm is dealing with. It's the overestimation problem. If we think that our Q value, our Q model, and our Q target model is just a lagged version of our Q model, then you can kind of imagine that our Q target model is not as good, right? Of course it's not as good. The Q model must be better because it's been trained for more iterations and it has more experience, right? That's the key idea. The Q model here is trained constantly. It's always better. The Q target is a lagged copy of my Q model, so it's never as good. But I'm doing right here, to compute our TD values, we do a max on my Q values, the Q values produced by the Q target. But if the Q target is producing Q values, I know that these Q values that the Q target produces is not as accurate as the Q values that my actual model would have produced, because the Q target is a lagged copy. It's not as good. And because it's not as good, its Q value estimates won't also be as good. And that means there's going to be some noise. It's not going to be as well defined as the Q values from our actual model. And that means when we take a max, we're essentially incentivizing an overestimation bias, right? We're always grabbing the max thing, even if it's wrong. And so this is a little bit of an issue and what double DQ learning solves. So what double DQ learning does is we decouple the action selection and evaluation. So first, going back to here, we still have to do all this. So to compute our current state action pair, we go ahead and pass in our current states, we compute some Q values for our current actions, and we get our current state action pair Q values, nothing fancy. What we're updating is this: how do we compute our TD target for the next set of states and the next actions, right? So we're essentially focusing on this. What we're doing is we're going to decouple the action selection and evaluation. Let's think about action selection first. I know that my Q value, my Q model here is better than the Q target because the Q target is again a lagged copy. So if the Q model is better, then why not go ahead and pass in my next states into my Q model and get some Q values, right? I'll get Q1, Q2, Q3, Q4 for my different things. And we're good to go. But this gets us back to the same problem. We were using, in our original setup, without having two different models, we're using one Q value, one Q model to estimate both my current states and my next states, right? This was doing both of them. So we need to use our Q targets to stabilize training. We still can't get rid of that. But I know that if I take a max on my Q model right here, which is better than the Q target, I know the max here is less prone to having some type of a bias compared to taking the max on my actual Q target, because the Q model technically should be better. And so what we do is this: we compute some Q values from our Q model, which is supposed to be better, on our next states. And so we get our next actions different Q values. We take the max here, but we don't use the Q value of this one here, because this again leads to the instability problem and the moving target. What we do is we say, oh, the second action seems to be the best as determined by my Q model. So if the second action is the best, why not grab the target Q value of the second action? So we're just essentially using this to figure out what's the best action. That's the action selection, but we're going to index that action in our Q target's predicted Q values, and that's our evaluation. And that's essentially all that's happening, right? So we're going to, instead of using, as we had done right here, we computed with our Q target, our set of actions, and we take the max over these actions, and we're good to go. But taking the max over our Q target model is not as ideal because the Q target is not as good as our Q model, right? At least theoretically. And so what we do is let's use our Q model to select our action, but we will evaluate the value of that action using our target Q value. So this model continues to be periodically updated. And so this remains a stable estimate for my TD target for me to minimize that mean squared error. But now I'm using my better Q model to decide what action do I want to take, but I use my more stable held constant model to actually give me a value for what that, the evaluation of what the Q value is for that state. And so we can, essentially that's the setup. Nothing fancier than that. And so again, 90% of the code to implement this is identical. So let's just do a super quick recap here. I bet I can just, there we go. So if you remember last time, this was the training step of our DQ learning, right? So what we did is for our DQ model, we go ahead and grab our Q estimate by passing in my current states into my model, giving my Q values for all the different actions. I then go ahead and grab the actions from those states, right? So torch.gather will go ahead and just index my Q estimates at the actual actions that I took, right? Nothing fancy. And then what we did is we grabbed our Q next estimate from my next model, DQN next. This is my target Q model. And then I went ahead and took the max over that. And this max here is what was leading to the overestimation bias, because this DQN next is a lagging copy of the DQN. So this DQN next is not as good as my DQN. And because this is not as good, if I take the max over it, it's essentially incentivizing an overestimation bias because I know that this model's not as good. There's going to be some error in it, at least more error than my actual DQN model should have. And due to that, we're incentivizing something that could be accidentally wrong, that overestimation bias again. So what we're doing is essentially just updating this little chunk of code. Everything else in this code is identical, right? So we have our, the trainer will be the same, our model will be the same, everything will be the same, right? Nothing is fancy or different. You can go ahead and take a look at that video if you're confused on any of this, so you shouldn't be starting here. So let's just go ahead and implement it. It'll take only a few minutes here. So what we're going to do is define our new train step for double DQ learning. We're going to do def train step. Let's make it a little bit bigger so it's easy for everyone to see. Train step. And this is going to take self and batch size, just like I did earlier. And so here's the setup. We're going to grab our batch. It's going to be self.time capsule. Right, we're going to go into our time capsule, and we're going to do our .access memories, right? We're going to access our memories, and we're going to be grabbing a batch size number of memories and making sure they're on the correct device, right? GPU. And then we can do if batch is none, return none, right? So if we don't have enough samples in our time capsule, like batch size number of samples in our time capsule, then we can't do anything. We just return none, and we just wait until we collect enough data. And so step one is we need to grab our Q value estimate, right, for the current state action pair. So that is this, right? So this part right here, to compute my QSA for my current states, right? We have to do that. So that doesn't change. So we can go ahead and do that first. Self.DQN, make sure it's in training mode. And we can do Q estimate is equal to self.DQN. And then we're going to grab from our batch the different states that we had. Go ahead and pass that in. And then our Q estimate is equal to actually it's going to be torch.gather. And what we want is the Q value of the actual action that we took. So we're going to go into our Q estimate, and we're going to index it for batch actions, right? Go ahead and grab those specific things. And we need to just add an extra dimension to it just so the indexing works out. Unsqueeze, -1. And we should be good to go. And all right, we need to also provide it dim equals -1. What we want to do it along it's a matrix of 2 dimensions, batch size by number of actions. We want to do it along the number of actions dimension, the second dimension. And then we're going to just go ahead and squeeze it again because we don't need that extra dimension once indexed. And so there we go. That is my Q estimate, my QSA for the specific state and for the specific state that I was in, current state, and the specific action that I took, right? And there we go. All right, and again, that's identical to what we had right here. What changes is this stuff inside. So what we're going to do is this is inference mode, right? So we need to inference these models. So with torch.noGrad, no need to compute gradients. First, we're going to use our actual DQN, the actual model that we're updating constantly, to estimate the values of the different actions. We're going to do next Q values is going to be self.DQN, and now we're going to pass in batch and our next states, just like that, right? So that goes ahead and does the first thing. So this is let's just refer to it as we go. That is this step right here. I passed in my next states into my model, and that produces my Q values, right? Some Q values here. And so now that we have that, we can do the next thing. Next actions is going to be torch.argmax, next Q values, dim equals -1, and we'll do keep dim equals true because we need that dimension for indexing. So this step right here is me finding out which action is the best one based on my better Q model, right? Which action is better? And that's my argmax, right? So which one is better? Which one has the largest Q value? Next, we do next Q values target is equal to self.DQN next, right? Next batch next states. So again, what I need is my different target Q values for that same set of next states, right? So we're passing the next states both into my Q model and to my lagging Q target model. So that's me doing this step right here, producing these Q targets right here. And then lastly, we need to do our max Q next estimate is going to be next Q values dot target dot gather along the last dimension index equals next actions. And again, dot squeeze -1 because we don't need that extra dimension anymore. And this line right here is doing what you see right here. I know that action number 2 was the max here, so I've indexed my target Q values for action number 2 because I want to use my target Q values as my value to minimize my mean squared error width to compute my TD target, but I want to use my better, more up-to-date Q model to actually decide the action. And that's again how we decouple the action selection and the evaluation of it. And so there we go. That goes ahead and computes that. Everything else is about the same. So TD target is going to be just our batch rewards, right? So standard formula, it's going to be rewards plus self.discount factor times our max Q next estimate. And then we're also going to have to multiply by, I believe I called it, yeah, terminal. So it's going to be our terminal state. So it'll be batch terminal, right? So we need to make sure that we mask out any terminal states because, of course, if the game is over, there is no next estimate, right? So we need to zero those specific cases out when the game is over. And so now our loss is going to be self.the loss function, whatever we decided, TD target with our Q estimate. And then we can do self.optimizer.0grad, loss.backward, and then torch.nn, this is just housekeeping, utils.clip grad norm. And we're going to do it on self.dqn.parameters, because that's the thing that's actually computing gradients, max norm equals 1.0. And then self.optimizer.optimizer.step, and then self.update epsilon, right? Because we have the epsilon greedy stuff happening as well. And good. So yeah, that's it. That's the only difference. So we're comparing to here again. In this setup, we used both the DQN next to grab our Q values, right, for the next states, and then take the max over it. But this leads to an estimation bias. So now what we do is we decouple it. We use our better model to figure out what action I'm taking, but then we use our lagged copy to give it the Q value that we want to minimize the mean squared error with. And this typically helps with stabilizing training a little bit more. Let's make sure there's, let's say, must have just misspelled something. So this should be, here we go. Batch states, yeah, states actions, yeah, plural. There we go. So it's training. It's not as interesting to watch a training loop, so I'll just stop that. It doesn't matter. You'll see it basically, increases as it's going. You'll end up with a lunar lander that lands reasonably well. So, nothing crazy. But that's basically it, right? So this is just one small extension of the deep Q learning method that we saw earlier to deal with that overestimation bias. So I will see y'all in the next one.